Hello. Now we are going to look at the standard deviation of a data set. And we can think of the standard deviation as being like the average distance between the mean of our data set, the middle of our data set, and all of the points, all of the numbers in our data set. Mathematically, that isn't quite what it is, but to get a feel for what standard deviation means, it can be helpful to think of it as the average distance of our data points from the mean of our data set. So we have two versions of the formula that we have to deal with. One of them is if we're given the data set directly, so just as a list of numbers, and the other one is if we're given a frequency table. And we can get both of them in the formula tables. So if we just have the numbers directly, what we do, if we look to our formula here, the square root isn't terribly important for our purposes right now. If we look here, we have x minus mu. And mu, the M looking letter, or it's a U with a tail, is the mean of the data set. So what we do is take the difference between each data point, each one of these points would be our data points, our x's, and we get the difference between each one of these and the mean of all of them. We square that, we add them all up, and we divide by the number of numbers in our data set, and then for mathematical reasons we take a square root of the whole thing. So that is what the standard deviation is. We're getting the difference between each one of our data points and the mean of our data set, and then we do something that's a little bit like a more complicated version of getting the average. So let's get into actually doing this. If we want to get the standard deviation, the first thing we need is the mean, the mu here. So to draw that letter, if we need to, it is going to be come up and then draw the letter U. And it's called mu. So we know the mean of a data set is just add up all the numbers and divide by the number of numbers. So we just have 7 plus 3 plus 1 plus 6 plus 3, all divided by the number of numbers. So we have 1, 2, 3, 4, 5 numbers in total. So our mean ends up being 20 all over 5. Our mean ends up just being 4. So the mean of this data set is going to be 4. There's no particular reason to expect that this ends up as being a whole number, or you can get questions where this is a unpleasant decimal. You just keep the decimal to 4 decimal places and you do your calculation throughout. In this case, we have a nice whole number to work with. So the standard deviation is going to be getting the difference between our mean and each one of our data points, squaring them, adding them all up. So our sigma, our capital sigma thing here, means that we add up the squares of the differences together. We're going to divide by the number of numbers, and then we get the square root of that whole thing. So sigma is our letter for our standard deviation, and we draw it kind of like a 6 that gets squashed down. And then we do our equal sign, and everything is underneath the square root. And we have lots of stuff to add up. So we need to get the difference between each one of our data points, each one of the members of our set. So 7 minus the mean, which is 4, to be squared. So x minus mu to be squared, our first data point, minus the mean, mu, to be squared. And then we're going to add up all of these for each one of our data points, plus 3 minus the mean to be squared, plus 1 minus the mean to be squared, plus 6 minus the mean to be squared, plus 3 minus the mean to be squared. And that's all going to be divided by the number of numbers, and there are 5 numbers in our data set. So when we tidy that up a little bit, we end up with 3 squared plus minus 1 to be squared, plus minus 3 to be squared, plus 2 to be squared. All we're doing is doing these sums in the brackets, plus minus 1 to be squared. divided by our number of numbers. And we get 9 plus 1 plus 9 plus 4 plus 1 all over 5. So we end up with 24 all over 5, or the square root of 24 all over 5. Which ends up being our standard deviation for our data set is 2.19. So again, we can think of this, it is not mathematically exactly what this is, but we can think of this as the average deviation, the average distance or difference between each one of our members of our data set and the mean of 4. It is not mathematically exactly that, but it is good. It is a good way to think about what it would mean. Now, what do we have to do if we are given this as part of a frequency table? That's very similar to the effect that calculating the mean has on the frequency table. We just have to count how frequently, we just have to multiply by how frequently we get each one of our outcomes, each one of our x's. And then your total number of numbers is just adding up the frequency of all of our outcomes. So we need the mean, just like before, we need mu, just like before, and when we're dealing with a frequency table, we have gotten 4 zeros and 5 ones and 9 twos and 1 3. So to get our mean, we're going to get our total value of all of our numbers, so we'd have 4 zeros plus 5 ones plus 9 twos. We could write all of these out in a big list, but there isn't any particular need if we know all of them put into our frequency table already. And then we just add up the frequencies of all of them, and that'll tell us how many numbers we have in our data set in total. And when we calculate that, we get 1.37. So here we didn't get a nice number like we did last time. It doesn't make any difference. We just make sure that we keep it as tidy as possible as we are writing everything out. Now we're just going to sub into our formula. So we're going to get the difference between our mean and each one of our outcomes, each one of our x's, and we're going to multiply each one of the squares of those by how often they came up. Sigma, big square root symbol, is going to be how frequently we get the first number. Well, we had 4 zeros, so it's going to be a frequency of 4. And then we get the square of the difference between our first value, 0, and our mean, 1.37, to be squared. So that's the frequency of that outcome, and then the outcome minus the mean squared, all multiplied together. And we do that for the other ones. We got 5 ones, so 5, and then we get the difference between 1 and our mean, and square that. We got 9 twos, difference between our mean, and square that. We got 1 3, difference between our mean, and square that. A little bit untidy at the end, but we can figure it out. And then we add up all of our frequencies to get our total number. And 4 plus 5 plus 9 plus 1. So we end up with our sigma is going to be 4 on minus 1.37 to be squared plus 5 on minus 0.37 to be squared plus 9 on, all I'm doing is tidying up these bits in the brackets so that if anything goes wrong, I can come back and see what I did. If I try and put all of this into the calculator at once, there's a very good chance I'm going to make an error, and I'll have no idea where that error happened if I try to put everything in all in one go. So we just do this a little bit piecemeal. And our total number of numbers when we add them all up is 19. And then we tidy all of this up. And we get the square root of 14.4211 all over our 19. And when we get the square root of that, we get 0.87. So what this would tell us is that this data set is less spread out than this data set is. The average gap, if we can think about it that way, the average distance, the average gap between our mean and our numbers in our data set is bigger for this data set than it is for this one. The gap here, the average distance between our mean and our numbers in our data set in this group is 0.87, and our average distance, our standard deviation here is 2.19. So this data set would be more spread out than this one on average. And that is how we calculate our standard deviation for where we have the data set directly and where we have it in a frequency table. And that is what we need for now.